Hello, my name is Anshkar and this is my I2 for the operating systems class. So today I'll be talking about energy efficient scheduling methods for real-time data transmission. So the motivation behind this was real-time apps need fast responses, and these devices are mostly, IoTs or our mobile phones, or it could be as small as a teleprompter, or could be as small as, a microphone, or anything, any small electronic device. So over here, in these devices, energy and memory, they're limited, and there is an always a inherent need to minimize energy consumption, because the lesser the better, the more efficient the system runs. So before this research paper, or before this method was invented, the older methods, they really didn't take buffer constraints into account. So their primary goal was to just send the data as fast as possible, which is nice, but it also comes at an expense of energy. So they weren't that energy efficient. So a solution to this is the maze AD model, which can do both. It can optimize your entire data transmission line. So we'll learn about that in a bit. So solution, as we talked about that, the maze ED method. So that method, you could think about it as a, uh, let's just say you have a lot of pins and you throw those pins on the ground. So it is like the shortest possible way you could wrap all those pins around. So it's basically a optimization problem, or like an optimization problem solver. That's the entire notion behind all this. So uh, moving on. So we have a look at the maze AD model. So moving on, we have a couple of constraints, which are the arrival curve, so which tells us about what all data is coming at the arrival. Then we have the departure curve, which tells us when does that data has to reach its source. Then you have the buffer, that is the minimum departure buffer limit, that is not buff t. And then you have a deadline, which is the minimum departure, which is, yeah, the deadline. And then you have minimum, that is the maximum uh, buff time and the deadline time. So from this curve, we can have a good look. So here we have our arrival time and we have our minimum departure time. So what the idea of this maze does is it manages your data transmission rate, for say. So it will make sure that the data packets that need to reach the end at the specific time reaches the end at the specific time, like no sooner or no later, because if it's faster, then you lose out on energy efficiency, and if it's later, then, well, you lose the data. So you don't want that as well. So that's exactly what this maze model tells you about. So looking at the maze model, so we have the AHSS algorithm, which works on the convex hull theory. So convex hull theory is nothing but finding the shortest path between two nodes. So even over here, we have a code that talks us about this HSS algorithm, but over here I've made a simple flowchart that tells us what the algorithm does. So from a very basic standpoint, what this does is at the very start, we will have our end and exit points. So we know when our data arrives and we know when the data has departure. So you have a straight line. Now what you will do, now if you have both the endpoints defined, you will transmit the data. Now, what happens if your data transmits too fast? You'll add a breaking point. So, what the breaking point does is it can either slow down the rate of transmission to conserve energy, or it can boost it if the data packets are lagging behind time. So you call that AHV and DHV respectively. So that is nothing but arrival, uh, help breakpoint, and it is departure help breaking point. So what they do is you add an AVH, sorry, when your data is traveling too fast. So it kind of slows your data down like a speed breaker, and you add a DHV when your data is moving too slow. So all this helps you optimize your your memory lane, or like the bus size, if that makes sense. So all you do is you look at your buffer constraint, you look at how much maximum buffer you can afford, you look at the arrival time, you look at the departure time, and then you transmit your data. And you do all this while keeping energy efficiency as your priority. So if we compare this, so we have a MRP that I talked about before. MRP tells us, or MRP, it doesn't tell us, but MRP is max rate procedure. So, well, that's very simple. What it does is it just transmits data at maximum speed. So it prioritizes speed over efficiency. And HSS, for that fact, it is a balance matrix. So as you can see, your energy for MRP is way higher than your HSS algorithm. Well, because again, one keeps speed as its primary focus, and other one keeps efficiency. For the same methods, we have a energy versus deadline graph. So as you can see, uh, the energy consumption is again way higher for MRP as compared to the HSS, because again it prioritizes speed, so it will always fulfill the deadline requirement, but at the energy cost. The same goes with the energy versus buffer size graph, where the buffer graph for the MRP is just too high, and it's kind of not ideal because you don't want to send the data very quickly, because there could be a possibility that you could be transferring data that does not exist. So it's kind of like a deadlock problem, if that makes sense. Then moving on, we have the conclusion. So from this research paper, what we have learned is how CHSS uses various different parameters as its boundary inputs, and optimizes and finds the lowest, um, or not the lowest, but like the least energy uh, required path. So like it finds you the most efficient path. And yeah, that's pretty much it. That was my I2. Thank you so much for watching.